We are going to finish section 12.1 today. 12.1 talks about Newton's second law of motion and relates acceleration to rate of change of velocity with respect to time, or relates acceleration to a change in momentum. So today, last time we talked about using Cartesian coordinates. Now we're going to do the same thing using tangential normal components and radial transverse components. And then we'll work some problems. So going over to the document camera, when we started talking about Newton's second law, which of course is the big deal in terms of dynamics, force is equal to mass times acceleration, where force and acceleration are both vectors. So in Cartesian coordinates, we could also say that a force, and let me do it this way. Force in the x direction is going to equal mass times acceleration in the x direction. Force in the y direction is equal to mass times acceleration in the y direction. Now we can also break that up in terms of tangential and normal components, which we discussed briefly in one of our first lectures. But in tangential normal components, instead of looking at our grid as being fixed, x and y, or horizontal and vertical, generally speaking, we're talking about something going around some sort of a curve. And whether or not that curve has a fixed radius, maybe yes, maybe no. But we have our components are the normal component, which we call E sub n, which is directed toward the center of curvature, and then E sub t, which is directed along the path of motion. So the E sub t represents all of the acceleration in the tangential direction represents all of the change of the rate of velocity change with respect to time. And the E sub n, or the normal direction, represents the change in direction. So as that point moves around the curve, whether the curve is a circle or some other type of a curve, the coordinate system moves with the point. So this is an inertial or relative reference frame. So we know, since force in any vector sense is always equal to mass times acceleration along the same direction, and we know that the acceleration in the tangential direction is equal to dv dt, and that the acceleration in the normal direction is equal to v squared over rho, where rho is the radius of curvature. We can then say that the force in the tangential direction, I shouldn't write that with that. I should just write it like that, since we've already defined the direction, is equal to the mass times the acceleration in the tangential direction, and that the summation of forces in the normal direction will be equal to mass times the acceleration in the normal direction, which is v squared over r. So the next piece of math, then, I'll just do this. I can take a look. Did I move that? I probably moved that too fast. So I'll pull that back up. So if we then talk about radial transverse components, and if you remember, we said there are some applications to machine parts for this type of a motion, but sort of the classical problem that we deal with at this stage is a collar sliding in and out along some sort of a radial arm. But if we have a point of origin O, and we have something that is moving, some point P, we can divide this up into a radial direction, the motion into radial and transverse direction. But the thing to remember, of course, well, now we're going to call this theta. Sorry about that. Here's my theta and theta. So when we do radial transverse components, theta is not the direction that relates to the change in the dv/dt term. It's just perpendicular to the r direction, which is directed toward the pivot point of that apparatus. All right, so we learned that this is sort of a mathematical expression. You can derive it, but it's, if you just start with the math and you say that the acceleration directed along that arm is equal to r double dot, or the second derivative of r with respect to time, minus the function r times theta dot squared. So in other words, the first derivative of theta with respect to time, quantity squared. And a sub t, I keep saying t, I apologize, it's a sub theta, all right, is equal to r theta double dot, second derivative of theta with respect to time, plus 2r dot, first derivative, plus theta dot. Okay, so if we combine that, we can then say force in the radial direction is going to equal mass times acceleration in the radial direction, or mass times r double dot minus r theta dot squared. And that force in the theta direction is equal to ma theta, or m times the quantity r theta double dot plus 2r dot theta dot. Right? So these are the equations that you'll use. And like I said, with these types of problems, you really have to rely upon the math to do the problems. Understanding the physical meaning of that is not as clear as it is, for example, when we use normal tangential components. So you always have to have, you'll have some function of r and some function of theta, and then you just do you take the first and second derivatives and work from that premise. Okay? All right. So that is the sum total of the lecture material that will be used to work your problems. And so for the rest of our hour together, I want to work some problems to sort of, first of all, I'm going to look at a couple of fairly classical dynamics problems that will help you with the xy, the Cartesian coordinates. And then we're going to look at a problem that's specific to a radial tangential, or a normal tangential and a radial transverse system of coordinates. Okay, so the first problem I'd like to work, let me make sure I didn't give this to you as homework. I'd like to work 1211, which I gave to you as homework. See, I love that problem. So I will work 12.12, which will get another classical approach. Now, 12.12 is a problem made up of train cars, and train problems, and especially the force on the coupling between train cars, are something that we spend a lot of time analyzing in dynamics. One way that we do it is we look at the train as a whole, and then we look at each car being acted on by the force in the coupling between the cars. So that's sort of a classical train problem. So when I look at problem 1212, we have a light train made up of two cars traveling 90 kilometers per hour. So we have car A and car B. And they're coupled together. Now, obviously that's overemphasized. In a real train, that coupling is going to be quite small compared to the way I've drawn it. But we have this, we're moving at a speed of 90 kilometers per hour. And the brakes are applied to both cars. knowing that car A has a mass of 25 megagrams, which is 25 times 10 to the 6 grams. Right? And car B has a mass of 20 megagrams. We wish to know, the braking force is 30 kilonewtons on each car. So if the car is moving this way, the force of the brakes acting on each car is going to be 30 kilonewtons. Okay. Determine the distance traveled before the train comes to a stop. Okay. And the force in the coupling between the cars while the train is slowing down. All right. So one of the things that's really good about problems like this is it kind of requires that you draw a really good free body diagram. So we can draw a free body diagram of the entire train, and then we can draw a free body diagram of the train's cars separately. And in this case, when we want to find the coupling force, we're going to have to look at one of the cars. It really doesn't matter if it's A or B in this case. We're going to look at one of the cars, A and B, and think of it as being acted on by this force rather than thinking of it as being part of a train with two different cars. So the force in the coupling really does bear the force on B. It bears all the force of A, and on A it bears all the force of B. All right, so if we look at it together, we know that our motion is going in that direction. I'm going to draw my little simple thing like this. We have this. We have a braking force here of 30 kilonewtons, braking force here of 30 kilonewtons, and we have our velocity going in this direction at a rate of 90 kilometers per hour. Right? So in the x direction, we know that the summation of forces in the x direction is going to equal mass times the acceleration in the x direction. So in this particular case, what are our forces? We have 30 kilonewtons and 30 kilonewtons acting that way. Since the train is in motion when it begins to slow down at a constant speed, there's no force acting on it that's driving it, right? I mean, we're talking about the minute that you cut the engine that you start slowing down, but you slow down with this braking speed. So the only forces that we really have are the 30 kilonewton force on the A and the 30 kilonewton force on the B. And that's going to equal the mass, which is 25 times 10 to the 6th. I don't like grams here. I'm going to change this in a minute. Plus 20 times 10 to the 6th grams times the acceleration in the x direction. Okay? Well, you can see from this, once I balance my units, I have one equation and one unknown. So I'm going to be able to solve pretty quickly for A. But I need to think about what that means in terms of units. If this is in kilonewtons, that would be 10 to the 3rd newtons, right? And if I'm looking at acceleration, and I would like that to be probably in base units of meters per second squared. If I go back to my original conversion that force is equal to mass times acceleration, we know that 1 kilogram times meter per second squared is equal to 1 newton. So if I write this in newtons and this in kilograms, I'm going to come out with the correct units, right? All right, so I'm going to call this 60 instead of kilograms or kilonewtons times 10 to the 3rd newtons. I just add them together, power of 3 kilonewtons to newtons. Here, I'm going to write this as 25 times 10 to the 3rd and 20 times 10 to the 3rd, so I can put it in kilograms. So I get 60 times 10 to the 3rd equals 45 times 10 to the 3rd kilograms times the acceleration in the x direction, or 60 times 10 to the third Newton over 45 times 10 to the third kilograms is equal to a sub x. 10 to the third cancels out. 60 divided by 45 is 4/3, 1.33. Newton per kilogram is dimensionally equivalent to meters per second squared. So the first thing I find is that the acceleration of these two cars as they slow down, and it's actually going to be, okay, so is this negative or is it positive? Well, my velocity is going this way and I'm slowing down. So technically, it's going the opposite. So technically, my velocity is negative. My acceleration is negative in the negative direction, which means it's positive. So, but if you just tell me slowing down or just some indication of that, it doesn't have to be rigorously mathematical. As long as I know that you understand it's not speeding up to come to a stop, that's fine with me. So, because we're engineers, right? That's the way it works. All right. So now we're talking, the next question is the force in the coupling, the distance. Okay. So let's take a look at just one of the cars. And it does not matter which car you look at. But if we look at A, we're going to be able to find a couple of different things. We're going to be able to see what the coupling force is. And so I would call that the force in the coupling. And we also have the force due to the brake. But this time, if we're looking at car A, the force in the brake is just the force on one of the cars. Everything else is going to be taken up in the coupling force. And my mass of A is just the mass of that car, and I already know I would like it to be in kilograms. So 25 times 10 to the third kilograms. All right, so I would like to find out how far it's going to be before it stops. And I would also like to find and I can do how far it goes before it stops with either of these. I could do it with this or with this. So let's do the coupling force since I'm here right now. Summation forces in the x direction, once again, equals 0. Only this time we're just looking at one of the cars. So my forces, I have a 30 kilonewtons. So I'm going to call that 30 times 10 to the third newtons, since I learned the last time, plus the force in the coupling. I have them both drawn the same way. Is going to be equal to the mass just of car A, 25 times 10 to the third kilograms, times the acceleration, which I know what that is as well, don't I? Which is 1.33 meters per second squared. Okay. All right. So another way to think about this, if you take the mass and multiply it by the acceleration, you can also think about that as being the inertia vector, which you talked a little bit about in one of the videos. But basically what that means is that this is what it takes, what you have to overcome in order to change its velocity. So that would be one way to look at it. Anyway, the force of the coupling then is equal to 25 times 10 to the third times 1.33, and that's in kilogram meters per second squared, which is newtons, minus 30 times 10 to the third newtons. So if I look at this number, 25, I can't do it in my head. I should be able to, but, you know, that's what happens. What is 20, just if somebody would tell me what 25 times 1.33 is? Yes, it's 33? 33.25 times 10 to the third newtons minus 30 times 10 to the third newtons tells me that the force in the coupling is 3.25 kilonewtons, or 10 to the third newtons. All right, the other thing is, I drew it this way, pulling on the car, right? And that means, because my numbers worked out, that is the correct direction, and it kind of makes sense if you think about it. It's trying to stop, car A is pulling it back. So is the coupling in tension or in compression? No, it's in tension. because it's pulling it backward. See what I mean? The car is trying to slow down, and B is pulling it backward. So I think, yeah, it's. I understand that though. It would be easy to do that the other way. All right. So then, in order to find the stopping distance, we can use kinematic equation. We're assuming that the velocity is that the acceleration is constant. So we can say, if we're looking for we can just do that. We know what our acceleration is. We know what our x minus x0 is because this is 0. We also know, this would be v0 squared. My v final is 0. So I get v0 squared equals 2 times the acceleration times x. Now, the only thing that we really need to recognize is that this is positive, this is negative, or this is negative, right? So we just need to keep our signs worked out a little bit. So we could say, see, that's a funny thing because when we get this 0 here, we can lose a sign in this pretty quickly. Anyway, but we can say that 2 times my acceleration, if I could consider that, I would consider that to be positive, times x, which I would consider to be negative because it's going in the wrong direction. Although the number's going to work out a little bit funny that way. Equals, what is my mass? It depends on which car I use. If I use this, I can just use the 25, okay? And then if I solve for this x, we'll get a value, that'd be squared. So I'm missing a, see, this is what always happens when I do these problems. We drop a sign this way, we bring that over, it becomes negative, then this has to be positive. So I should just stick with that. 2 times a, so this is positive with my sign. X minus x0, x is actually positive as well. So then this is what's going to come over as a negative in order to solve for that. Does that make sense? No, I don't like it. I liked it the original way I set up. All right, so let me just rewrite this. I have v squared minus v sub 0 squared. That's where I'm going to get this. This is where my sign's going to come from. Equals 2a times x minus x0. I'm going to do it like a mathematician this time. So my final velocity in this analysis is equal to 0. So when this comes over, it comes over as a positive. And this is where I have to think about, if I consider this to be positive, then this is going to be negative. In other words, I would have to set up my coordinate system so that x in this direction is positive. Or I could call this position, in other words, I could say x sub 0, where I start, is to the left, and so I could consider this to be negative. So I'm going to call it like that. From a mathematical point of view, that makes more sense. But we're solving for x, right? That means that we're solving for x to the left of the starting point. All right. So having said that, we know that our initial velocity is 90 kilometers per hour. And we need to change that into meters per second. So we get 1,000 kilometers. 1 kilometer per 1,000 meters times 1 hour per 3,600 seconds. And so if I take 90 and multiply it by 1,000 and divide it by 3,600, I will get that velocity in meters per second. That's going to be something like 25. Do you guys have, somebody have a calculator? We take 90 It's 25? Okay, thank you. So we get 25 squared plus 2 times a times that negative x, which is, oh, this isn't my, that's my 25. And then my x is what I'm looking for, minus x. All right, so then if I bring this over to the other side, I get x times this quantity equals 25 squared, and I can divide by that, which is 2.67. So if I take 25 squared, which is 625, I think. All right, and then divide that by 2.67, what do I get for a distance? 234. Okay, let's see, 235-ish. All right, and then let's just check our units. This is meters squared per second squared. And so if I put that in meters squared per second squared, which I did, and I put this in meters per second squared, and then this unit is going to come out in meters. Okay. So whenever you have a train problem, that's basically the method of attack, is to look at it as a whole unit, and then to just look at one car with a force acting on one car through the coupling. All right. You guys have any questions about that? All right, well, I have one more problem I wanted to work with, sort of coordinates, the same sort of coordinates, but I'm going to switch gears and talk about a normal tangential problem. Oh, sure, yeah.
If you want to calculate the force in B as well?
It's going to be exactly the same.
Oh, really?
Yeah,
Even
exactly.
though the masses are different?
Yes,
Oh.
yes, that's kind of the thing. Is it'll come out to be. I understand what you're asking, but yeah. So the force in a coupling is an equal and opposite force. So it's either going to be in tension or in compression. So the direction is going to change. So in other words, if you're in mechanics of materials, do you remember that? Yeah. So it's going to do exactly that same thing. So it's an excellent question. Excellent question. Otherwise, it will blow up. So, which is never a good situation. So, there we go. All right. So, let's take a look at the next problem. I'm going to work as 1237. I want to see which is in normal tangential. I want to look at which one it's similar to for you. Okay, so I'm doing 37, and I'm asking you to do 36. So the setup is quite similar. Your problem is a tether ball, and mine is an athlete throwing a hammer. All right, so 1237. The problem says we have an athlete, and I'm just going to draw this, okay? So he has a hammer, and he's throwing, or he's spinning it from point B to point C, which is the center, more or less. And as he spins the hammer, it describes a circle, or I don't know if it's exactly a circle. Yeah, horizontal circle. Okay. It says that, so in other words, the hammer's going to go all the way around like that. So from the center of the circle, the distance to the hammer is always rho. Call that point O, so don't confuse it with C out here. And it says it gives me an angle here, too, of theta. Right? So during a hammer's throw, we have 7.1 kilogram head. So the mass is 7.1 kilograms. All right? And it revolves at a constant speed. So V is a constant in a horizontal circle. We're told that the radius of the circle, which is also the radius of curvature, is 0.93 meters, and he keeps it at an angle of 60 degrees. Determine the tension, which is the force directed this way, right? So not toward the center of the circle, which is interesting. So we're directing it toward the, well, I guess it is, the way I have it drawn, it looks crazy. He can't really spin it that way, can he? So let me draw this again. You will find this is my biggest remediation point, is not being able to draw a circle. So we have rho, it looks like that, 0.93, and that means he has to be quite tall and spin it from up here, and that angle is 60 degrees from here to the horizontal circle that he's spinning. All right, it's a little bit better, and it still weighs, or still has a mass of 7.1 kilograms. Right, so there we go. So the question is, what is the tension along this wire? Well, if we take a look at the hammer, and we can think about what are the forces acting on the hammer. We have the tension that is acting along this trajectory from the center of the hammer to the hands of the thrower, and that's what we're looking for, is what the value of that tension is. And we also have the weight of the object, the weight of the hammer that's acting down. Now, along here, along that horizontal circle, is where we have the acceleration, right? And the acceleration is actually that normal acceleration directed toward the center of this circle. So it's going to be m times v squared over rho. That's the acceleration in this direction. All right. Now, the problem with that, or I don't know if it's a problem exactly, but the tension is not directed along that. And since this is a vector solution, we're going to have to kind of do some funky thing with our coordinate system. So if we look at the summation of forces in the y direction, since it's a horizontal circle, there's no acceleration in the y direction. Okay? So if we consider that, we can then say, well, what's the component of tension in the y direction? And that's directed upward, and it's the tension in whatever that is. Do we have a number BC times the sine of 60 degrees. So that's the component of TB that's acting upward in the y direction, minus the weight of the ball, and those two things added together equal 0. So I can then say that the TBC times the sine of 30 degrees minus the weight, which is equal to the mass times gravity, is equal to 0. So just going back here, if we look at this, the weight is equal to mass times gravity, is equal to 7.1 kilograms times on Earth, which we're assuming he's on Earth, 9.81 meters per second. So if I take 7.1 and multiply it by 9.81, what is my weight in newtons? (7.1) times 9.81, somewhere in the vicinity of 70-ish, 69.65. Okay, so the weight is 69. I'm going to carry out 6.5 for right now. I'm going to get rid of it, sine of 30, when we figure that out. So then we get TBC equals the weight, 69.65 newtons, divided by the sine of 30 degrees. Okay? And the sine of 30 degrees is a half? Yes! So we get 69.65 newtons divided by 0.5, which is the same as multiplying by 2, right? So this turns out to be just under 140, 139.7, maybe? Is that right? (139.3), 653. There we go. Newtons. So I would say to significant figures, the mass is given with two significant figures. So I would like to report this with two significant figures. The tension in BC is equal to 140 newtons. All right, so what is the speed of the hammer's head? So in other words, the next part is we need to look for the velocity. Well, now we can just go back to the circle. We're not talking about this tension anymore. We can just talk about the v squared over r. So to find the speed of the hammer's head, I guess we're going to have to do a little bit of, well, let's see. In the x direction. We did y, so now let's do in the x direction. Now, in this particular case, that's going to equal the mass times the acceleration. This time, the acceleration is going to be part of the acceleration that's in, how do I want to think about that? Oh, all right. So the force in the x direction is going to be the component of. It's not a forceless thing, is what I was thinking of it. It's going to be that component of the tension. So if we think about it, here's my tension, and the tension is going to be directed upward, and so there's actually a center-seeking force, which is called a centripetal force, in the x direction, which is where the action occurs. So it's equal to mass times that normal, or the radial normal acceleration, v squared over r, and the force is going to be the tension, if this is 60 degrees, times the cosine of that angle. All right, so we discovered that the tension, I'm going to go back and just use 130. See, I'm still stuck on 130. This would be 139, 140. Yeah, that's okay. I'm going to use 139.3 right here, just to not lose anything due to rounding, times the cosine of 60, which would be rho, times rho divided by mass is going to equal the velocity squared of that hammer. Okay, so I know that rho is 0.93 meters, and I can solve for the cosine of 60, which I think is 0.866, but I don't remember. Have the tension of 139.3 newtons, and the mass of that tells me that that's equal to v squared after I work out my units. Okay, so if I take 139.3, multiply that by the cosine of 60, doesn't look right to me. Is the cosine of 60 equal to 0.5? That doesn't look right. Somebody's going to have to do it for me. All right, then it is. I just have it in my head. I'm thinking of the cosine of 30, I guess, but it's 0.5. So, all right, so we have 139.3. If your calculator says that it must be true, right? Times 0.5 times 0.93 meters divided by 7.1 kilos, and I get a v squared value of, is it 9.1? Okay, 9 point, since I'm going to take a square root here, I'm going to keep it like that for a minute. We need to check out our units. So we have Newton meter per kilogram. I know from Newton's second law that a Newton is a kilogram meter per second squared. So I can put that in instead. Kilograms cancel, and I'm left with meters squared per second squared, which is a terrific unit for velocity squared. So that means my velocity, when I take the square root of that term, is going to be in meters per second. And so it's just over 3, right? 9. How many? 3.02 meters per second. And so that means that the velocity in significant figures, if we're going to keep 2, is going to be 3, not just 3, but 3.0 meters per second equals the velocity. Okay. All right. Any questions? So I am out of time. All right. Well, there we go, ladies and gentlemen. So that will be it for today. There's also there's at least one problem on your homework that has to do with radial transverse components. So you can work it out the same way. Once again, it's going to be a little bit stricter in terms of the math. So just make sure that you have that, but we can spend a minute when we get back to class on Friday, or when I record on Fridays, talking about that as well. All right, we'll see you guys then.